So I will repeat for the second chord, okay? For the second chord, I take first this part, okay? This part is a C minus a certain constant that I will call H, okay? This part also is a constant, so I can add plus a constant C1. This part here, from this point to this one, is SB, so it's plus SB minus another constant H prime. And finally, this is a constant. That's it. So I'm done with this part. So this is equal to constant, okay? Now, since H prime, and C1 all are constants, I can take them to the other side of my equation. And I will have for my second chord that S of B plus S of C is a constant. Okay? And now if I derive this relation, I get that VB plus VC equals to 0. And if I divide another time, I get that AB plus AC is 0. So in this way, I was able to relate motion of B and C, okay? Now, going back to my other equation, and given that VA is given, so they told me that A is pulled downward. Since A is pulled downward in the positive SA direction, so I know that VA is equal to plus 2. Okay? And now, by applying the two equations that I got, I derive them. If you want, you can, before deriving your equations, you can eliminate S of C between the two equations. Why? Because you have information about motion of A, and you want to deduce motion of B. They didn't ask you to get anything about C. So one strategy is or to derive these two relations, then eliminate VC between the equations, or you can eliminate SC before moving to the derivative. So if you want to eliminate SC between the two, you can say that from equation 1, SC can be substituted by L1, which is a constant, minus S of B. And then when you replace in your second equation SC by this value and you develop, you will get that SA plus 4SB equals to L2 plus 2L1, which is a constant. And now, after eliminating SC between the two equations, when you derive this relation with respect to time, you get that VA plus 4VB equals to 0. So you can deduce that VB is equal to minus VA over 4. And since VA is given to be plus 2, so you deduce that VB is minus 0.5 meters per second. The negative sign for VB indicates that B is moving upward because SB is down. The positive coordinate direction is downward. So if you got a negative result, this means that you are moving in the opposite direction to the positive SB. And this is expected because when A will move down, B will go up. Okay. Any question on this problem? Okay. So this was the part on pulleys. You have several practice problems on system of pulleys in the review problems. So please start to go over review problems to prepare yourself for the exam. Now, another problem, an extra problem also on pulleys. In this problem here, we have a man is hosting a safe ass by walking to the right with a constant velocity VA equals to 0.5 meters per second. Determine the velocity and acceleration of the safe when it reaches the elevation at point E. The rope is 30 meters long and passes over a small pulley at point D. So in this example, we have the following. We have a block S that should be lifted upward. It's moving vertically. And this is done by the motion of a man in the horizontal direction. Okay, please here pay attention. Whenever you select a coordinate, your coordinate should not have variable direction. So a common error here would be to say, for this part, I will say that S is moving vertically. So I will take, this is the first coordinate. I can take it like this. So this is S of C. Or also, if I take the ground as my reference, which is fixed, I can do it. I can take an upward coordinate of Y. Both are right choices. Now, what will be a wrong selection is to say that for this part of cable, I will take D as reference, and I will take DA as my coordinate. Can you tell me why this choice is wrong? Why I cannot take the coordinate here like this?
Because it's not only moving, it's also the angle between
Exactly.
CD and AR is changing.
Very good. This angle is changing, okay? And your coordinates should be along fixed directions, because if your coordinate is changing in direction, when you derive, you should take into consideration not only variation of magnitude, but also variation of direction, which will be much more complex. This is why you always select directions that are not changing. And here, A is moving horizontally. So a good choice for the second coordinate will be to take a horizontal coordinate of A, which will repair the position of A. Okay? Now, if we consider these two coordinates, so this is X of A, coordinate 1, and Y of C is coordinate 2, I will try to express the total length of my chord function of these two coordinates. Okay? If I look at my chord is divided into two parts, CD, so this is part 1, and DA, which is part 2. Okay? And I will express both lengths 1 and 2 function of my variables. What is length 1 function of my Y? If you look at your figure, okay, the level of D from the ground is given. So D is at 15 meters from the ground, okay? And CD is 15 minus this part, which is Y. So I can say that L1 is equal to 15 minus Y. Now, what about L2? What about L2? How to get L2 function of my variables? What should I do?
Trigonometry, يعني we should use cosine and sine.
Oh, Pythagorean theorem, it's easier. Okay, you can apply Pythagorean theorem. You say that this length here is in a right triangle. This is my right triangle. Okay, my right triangle has here a fixed length of 15 meters, has here a horizontal side equal in length to x, and I have the third side is AD. So I can write that AD square, which is equal to L2 square, equals to x square plus 15 square. Okay, so I can say that L2 is radical of x squared plus 15 squared. Okay, and now once I expressed my L1 and L2, the next step will be to say that the total length of my chord is a constant. So I will write now that L1 plus L2 is a constant, and this constant is equal to the length of my pulley. And they told me the pulley D is very small, to neglect this small part, the arc of circle. Because the radius of the pulley D is very small, I can neglect, so L here is nearly 0 for this part. So I can say that L1 plus L2 is equal to the total length of my chord, which is 30 meters. Now, I will replace L1 and L2 by their values. L1 is 15 minus y. L2 is radical x squared plus 15 squared. And this is equal to 30. Now, in general, when we find the relation for the chord length, we derive, okay? But do you think that, can I modify this form to have an easier derivative? Instead of deriving a radical, I can transform this equation to another one that is easier to derive. What can I do? Always try to avoid radicals and to avoid the fractions in your derivative. So if you take 15 minus y to the other side, what do you get?
Square both sides.
Yeah, and you do square for both sides, okay? So if I take 15 minus y to the other side, I get, then for the other side, I get 15, which is 30 minus 15 plus y, okay? And if I do square for both terms, I get that x squared plus 15 squared is equal to 15 plus y squared. And this is a form that is much easier to derive, okay? So let us derive together this relation to get a relation between velocity of A and velocity of C, okay? So I will write it again, x squared plus 15 squared equals to y plus 15 squared. Now let us derive with respect to time. The derivative of this term is 2 times x times dx by dt. So I'm using the chain rule. This is a function of x. I derive first with respect to x. It will give me 2x. Then I multiply by dx by dt. So I get x dot. Okay. Now 15 squared is a constant. So the derivative is 0 equals to, for this term, when I derive this function, I will also use chain rule. I derive first with respect to y, then I derive with respect to time. The derivative with respect to y is 2 times y plus 15 times dy by dt, because the derivative of this function with respect to time is dy by dt, which is y dot if you want. It's y dot. Now, x dot represent what? X dot represents the velocity of A, and y dot represents the velocity of C. So in this way, I was able to relate velocity of A to velocity of C. Okay, and in particular, they told me what will be the velocity of C when I will reach an elevation of 10 meters. So I want to find velocities at this position. Now, VA is a constant. It's not changing. However, VC is varying. How can you explain this? VA is not changing in magnitude, but VC is changing in magnitude. Due to what? Because this angle is changing, okay? The change of this angle will create a varying speed for C, while VA is maintaining a constant speed, okay? So here, if you just replace VA by 0.5, okay? You have Y for the particular examples. I want, what is VC for Y equal 10? So I replace Y by 10. And to get the corresponding X for Y equal 10, to get what is X at this level, you just replace Y by 10 here. If you replace Y by 10, you get what is the corresponding value of X. And then you plug it in this equation to get VC at this position. Okay. Do you want me to repeat anything here? Is it clear? Okay. So now we were able to find a relation between velocity and of A and C. I will write this relation again and derive it to get a relation between accelerations. Okay. So we said that 2x times x dot is equal to 2 times y plus 15 times y dot. Okay, so this is the velocity relation. Now, because x dot is constant, it's equal to VA, you can replace it directly by its value. It's not varying. Okay, I will do for you a general case. If it was varying, what will happen? And then for the case of constant VA, what should we do? Okay, so now to get accelerations, I derive a relation between accelerations. I derive this relation with respect to time. Okay, so first I have here is a product of two functions, u times v. 2 is, you can simplify 2 from both sides. So you get x dot equals to y plus 15 y dot. Now deriving the first term, okay, you have derivative of x dot is x dot. So this is u prime times v, so times x dot again. So this is x dot square, okay, plus uv prime, u is x, v prime is the derivative of x dot with respect to time, which will give you x dot dot. Okay, this is equal for the from the other side too. Here also you have the product of two functions, u times v. So if you derive u prime is y dot, and since v is also y dot square, you get y dot square plus uv prime, which is y plus 15 times the derivative of y dot with respect to time, which is y double dot. Y double dot represents the acceleration of C. Okay, now x dot dot represents the acceleration of A. But since in this particular example, they told us that VA is constant, this means, because this is constant, this means that no acceleration for A, and I can cancel out this term. Okay, so then my final relation is the following. X dot square represents the velocity of A. So VA square is equal to y dot is the velocity of C. So it's equal to VC square plus y of C plus 15 times the acceleration of C. They want me to get at the corresponding position at y equal 10. What is AC? It's my only unknown now. I replace y by 10 here. I already got from previous step what is VC for this position. I replace it, and VA is given to be 0.5. The only unknown in this equation is the acceleration of C. So I can calculate for y equal to 10 meters, what is the acceleration at C? Any question on this problem?
بروفيسور
نعم.
بس الاكس دبل دوت ليش شلناها؟
لأنه x double dot represents the acceleration of the man. And they told us that the man is moving at a constant velocity of 0.5 meters per second. If your velocity is constant, your acceleration will be 0, since you are moving along a rectilinear path.
Okay, thank you.
Welcome. Any other question? Okay, so this is for police systems. Now we will move to the last section of this chapter, and this is the longest chapter in this course. Okay, so you will see that 13, 14 are much simpler if you want. They are compact chapters, and this is a key chapter to understand the others. So please make sure you understand all concepts in this chapter. And if you have any questions, we can do Zoom online meetings whenever you want to go over your questions, or you can send me directly your questions by WhatsApp, as you prefer. So the final section here is relative motion, and this is a relatively simple concept. Okay, what is the idea of relative motion? In relative motion, I can measure velocity and acceleration of a particle with respect to a moving frame, instead of measuring it with respect to a fixed one. Okay, so for example, let us say you have a car. So let's say you have a car, or the man A is on his bicycle or motor, whatever you want. A is moving, okay, and I'm considering a frame attached to A that is translating. Okay, so you have a translating frame and a fixed one. Now, if you have another particle B that is moving, you can measure its velocity, or with respect to the fixed frame, or with respect to the moving frame. Okay, and we can relate these measured velocities. To be able to relate measured velocities, we will first relate position vectors. Okay, if I want to measure the position of B in a fixed frame, I should take as position vector OB, which is starting from the reference of from the origin of the fixed frame to particle B. Okay, while if I want to characterize position of B with respect to the moving frame has an origin at A, so the position vector will be R of B relative to A. So this symbol, when you see RB/A, means position of B measured by point A. Okay, so if you look at your figure, you can see a triangle of vectors that can allow you to relate the position of B measured in a fixed frame, the position of B measured with respect to a moving frame, and the position of origin A of the moving frame. So the moving frame is attached to A, and A is moving. So to detect position of A in the fixed frame, I need to know what is vector RA. Okay, and looking at these vectors, you can simply say from geometrical rule that vector position RB is equal to vector RA plus RB relative to A. Okay, keep in mind also the frame should be translating the moving one. I will tell you why in a while. Okay, so you cannot at this stage take a rotating frame. The frame fixed to A should be translating. In next chapters for rigid body analysis, we'll see what will happen if we take a rotating frame. But now for particles, we'll just limit ourselves to a translating frame. So the idea is now that I related positions of B measured in a fixed frame and a moving frame. And now, if I derive this relation with respect to time, I can relate velocities. When you derive RB with respect to T, you get VB. And this velocity is measured in which frame? When you derive this position vector, you get a velocity measured with respect to which frame? RB represents the position relative to what? To O, which is the center of a fixed frame. This is why when you derive this position vector, you get VB into the fixed measured by fixed frame. Okay? Now, if you consider the derivative of RA, RA represents the derivative of vector OA with respect to time. Okay? And since OA is measured with respect to O, which is the origin of a fixed frame, when you derive RA with respect to time, you get the velocity of A measured in the fixed frame also. Okay? However, when you derive this term here, you are deriving a position vector relative to A, which is the center of a moving frame, of a translating frame. So when you derive this, you will get the velocity of B relative to A. Now, why I told you that the frame should be translating? Because if you remember, when we did analysis together, okay, any frame, any unit vectors that are changing in direction, when I do derivatives, I should derive also these unit vectors. However, if the unit vectors are not changing in direction, the derivative will only take into consideration the magnitude of relative velocity. Okay, so I can say that this is why here, to not have complex derivation, I consider a translating frame. So IJK will remain parallel to themselves, and just I have to derive the RB relative to A, okay, without considering the derivative of I, J, and K. So if I derive this relation, I will get the following. I will get that VB equals to VA plus velocity of B relative to A. And if I do interpretation of this relation, VB is the absolute velocity of B. When I say absolute velocity, this means that this velocity is measured with respect to a fixed frame. VA also is the absolute velocity of A. So both are absolute velocities measured relative to the fixed frame. However, VB relative to A is measured in the translating frame. So this is a relative velocity. Okay, this is a relative velocity. And then I can say that if I derive again this relation, I can relate accelerations. So if I derive again with respect to time, I get that acceleration of B is equal to acceleration of A plus acceleration of B relative to A. And here also AB and AA represent absolute acceleration measured in the fixed frame, while AB relative to A represents the acceleration of particle B measured with respect to the moving frame. Okay, so that's it. In this section, you should just know two relations. VB equal VA plus VB relative to A, and AB equals AA plus AB relative to A. Now, let us do a small example on this to see how to apply it. So for example, here, you have a train traveling at a constant speed of 90 km/h, crossing over a road. If car A is traveling at 67.5 kilometers per hour along the road. Determine the magnitude and direction of relative velocity of the train with respect to the car. So in general, they can ask for relative velocity value. To get this value, you should do difference of absolute velocities, because here we have two objects, the train and the car, okay? And the question is to get the velocity of the train relative to the car, okay? Using the relation we developed now, we have that Vt relative to A is equal to velocity of the train minus velocity of the car, okay? Because if we write it in the way given in the course material, we can write that the velocity of the train can be decomposed into velocity of the car plus velocity of the train relative to the car, okay? So here we'll do exactly, we'll use exactly this formula, but because we have Vt and Va absolute, we can get the relative one. So the relative velocity is the difference between velocity of the train and velocity of the car, okay? And now, since they gave me direction of motion for the train and direction of motion for the car, I can get my vectors V train and VA in the absolute frame. The absolute frame is a frame fixed to the rod. It's characterized by unit vectors I and j. All I have to do is to express my velocities in this frame. So as you can see, the train is moving horizontally and with a magnitude of 90 kilometers per hour. So it's only along I. So I can write that the velocity of my train is just equal to 90I. Now, to express the absolute velocity of the car, I look at my figure. The car is moving along this direction, okay? And this direction is doing 45 degrees with the horizontal. So to get the vector VA, I should decompose it into two components, one along I, one along J. And since the magnitude is given, so I just have to write VA equals to 65.5. No need to change units because both velocities are given in kilometer per hour. So your final result of V will be in kilometer per hour. You can keep same units here. But if units are different, you should convert to one common unit. So you have 67.5 times cosine 45 along I and plus 67.5 times sine 45 along J. So as you can see here, you have now the vectorial expression of your velocities. All you have to do is to apply the rule that velocity of train relative to A is the difference between Vt minus Va. And then you can get your relative velocity vector. Since they asked for the magnitude and direction, for the magnitude, you do radical 42.3 square plus 47.7 square. Now for the direction, as I told you, whenever they ask for direction, you draw your system. You say, I'm in which quadrant? I have positive I, negative J. So I am in the first quadrant. So this is V of t, velocity of t relative to A. This is the vector. And then I can just get this angle alpha. I say that alpha is tan minus 1 of the absolute value, okay? Because here I have a negative sign, so I'll just take the absolute value of minus 47.7 over 42.3. And in this way, I get my angle alpha. And I will be done with the velocity of the train relative to the car. Okay? Any question on this?
Oh, thank you, Professor.
Okay, thank you. Bye bye.
Thank you.